Question 50. I really like question 50. I thought this was a fun one. It's not a question that relies on you knowing some obscure theorem. You just have to be a little bit clever and apply some knowledge from, I don't know, like a Calc 2 class, I guess. So what's going on here is we have this double integral. We want to first integrate e raised up to the y squared power from 2x to 2 with respect to y. And then we want to take that answer and integrate that with respect to x from 0 to 1. Sounds easy enough, right? Well, the problem is e raised up to the y squared power. I kind of wish they had put parentheses there because exponentiation is not associative, but whatever, that's just me being picky. Anyways, this thing does not have an antiderivative with respect to y. That's a little bit of a lie. It does have an antiderivative. It just doesn't have an antiderivative that you can write. It does not have an elementary antiderivative. In fact, it's a fairly famous counterexample that shocks a lot of Calc 2 students because in Calc 1, any elementary function has an elementary derivative. So when you're taking Calc 2, you expect any elementary function to have an elementary antiderivative. But in fact, that's not the case. Relatively easy looking functions like this one don't have elementary antiderivatives. So we can't take the antiderivative e to the y squared with respect to y. So how in the world are we going to figure out this problem if we can't figure out this part right here? Well, the trick is to just switch the order of your integrals. Instead of integrating with respect to y first and then integrating with respect to x, integrate with respect to x first and then integrate with respect to y. If you're going to do so, you have to be really careful about the bounds. Let me draw you a picture. What's going on in this original problem is our x value is ranging from 0 to 1, so from here to here, and our y value is ranging from twice our x value up to 2, so from some moving point up to 2. When our x value is 0, our y value starts at 2 times 0, in other words 0. When our x value is 1, our y value starts at 2 times 1, in other words 2. And at any point in between, it starts on this line right here. What I'm saying is the region that we're asked to integrate over is just this region shaded in purple. Instead of first saying that the x goes from 0 to 1 and then defining the y's in terms of x's, we can first say that the y goes from 0 to 2 and then define the x's in terms of y. So for an arbitrary y value, where do our x's range from? Well, it looks like they always start at 0 and they go up to this point. Because this point is on this line, we know its y coordinate is double its x coordinate, and therefore its x coordinate is 1/2 of its y coordinate. What I'm saying is we want to integrate from 0 to y over 2. By rewriting our problem this way, we'll be able to evaluate the integrals just using elementary methods. Let's do it. We'll first look at this integral and note that the antiderivative of e to the y squared with respect to x just amounts to the antiderivative of a constant, and the antiderivative of a constant with respect to x is always just going to be x times that constant, e to the y squared power. We need to evaluate this thing from 0 to y over 2. If I change all the x's into y over 2, I get y over 2 e to the y squared power. If I change all the x's into zeros, I just get 0. All that's left to do now is evaluate this integral with respect to y. Note that we can do that with a u substitution. We'll let u be equal to y squared, in which case du is equal to 2y dy. We don't have a 2y dy, we have a 1/2 y dy. So maybe we'll multiply both sides by a quarter and get 1/4 du is equal to y over 2 dy, and then do our substitution. The 1/4 can go out in front of the integral symbol. I'm going to evaluate from y equals 0 to y equals 2. I don't feel like rewriting these endpoints in terms of u's. The y over 2 is gone, the dy is gone. Those both changed into this 1/4 du. And instead of writing e to the y squared power, I can write e to the u power. This is my favorite integral to evaluate. I don't know if that's really true, but I can pretend because the antiderivative of e to the u is just e to the u. So all I got to do is evaluate e to the u from y equals 0 to y equals 2. I'll switch my variable back to y, so I get 1/4 e raised up to the y squared power. Evaluate it from 0 to 2, I get 1/4 e to the 4th minus e to the 0 power, but e to the 0 power is just 1, so I get e to the 4th minus 1 over 4. Come up here and look at your answers. It looks like that is answer E.